chi-squared test for homogeneity. The chi-squared test for homogeneity is a test used to determine whether frequency counts are distributed identically across different populations. In other words, whether equal proportions exist in a series of populations. The null and alternate hypotheses are H0 is the distributions are the same, HA the distributions are not the same. The conditions for the chi-squared test for homogeneity are each sample is a simple random sample from its respective population. Each population is at least 10 times as large as the respective sample. The variable we're interested in is categorical, and the expected frequency count for each value is at least 5. We conduct this test much like our chi-squared test of independence. The formula for our expected count is row total times column total divided by n, where n is the grand total of all values. The test statistic is the sum of the observed minus expected squared divided by expected, and our probability is the probability that chi-square is greater than this test statistic with the degrees of freedom of rows minus 1 times columns minus 1. For example, suppose we've conducted a study to determine the TV viewing habits of men and women. A simple random sample of 250 adults, where 100 are men and 150 are women, was taken, and these are their results. We want to test at the 5% significance level to determine if the men's TV preferences are different from the women's. So in this case, our null hypothesis is that the men and the women are the same. So our distributions for our TV shows are the same for men and women alike. And our alternate is that the distributions are different. So these values in this list right here, these are all my observed counts. And they're all over 5. And we're assuming these are from different populations and that we meet all of our conditions. These values over here are our row totals. And these values going across are our column totals. And this value right here is our grand total. Our degrees of freedom is our number of rows minus 1 times our number of columns minus 1, which will be 2 for this problem. Now we have to compute our expected counts. So our expected counts will have men, women, and we'll just continue from above. So for the black list with men, we're going to do 100 times 90 divided by 250, and this gives 36. For American Idol, that's row total of 100, column total of 77. This gives me 30.8. For NCIS, we have 83 times 100 divided by 250, which is 33.2. And then let's repeat for the women. Row total for women will be 150, column total 90, divided by 250 is 54. American Idol, we have 150 times 77 over 250, which is 46.2. And last, for NCIS, the women, we have 150 times 83 over 250, which is 49.8. Now let's let the calculator do our work for us for our test statistic. So what I'm going to do is I'm going to enter my values for my observed and my expected in two different lists. Now these are actually in arrays like this, but to keep it easy, we're going to do lists, and I'm going to go across however you enter your first list. You need to make sure everything corresponds in your second list. So we're going to go stat and edit. And what I've listed in L1 is my observed counts, and I went across the rows. So looking back at this, 40, 15, 45, you can see where they correspond going this way, and then I did the 50, 62, 38. And then my L2 would be my expected, 36, 30.8, 33, then 54, 46.2, 49.8. So I've entered all those values. Now what I'm going to do is I'm going to have L3 calculate for me my observed minus expected squared over expected. So I'm going to arrow over and highlight L3, and I'm going to push enter, and I'm going to do parentheses. My observed are in L1, so we're going to call up L1, second one, minus my expected are in L2, so second L2, close your parentheses, squared, and then we divide that by our expected, which are in L2. Now when I hit enter, it fills up L3 with the values for each observed minus expected squared divided by expected. Now our test statistic will be the sum of all these values. So let me quit out of here, and I'm going to go to list, which is second, stat, and over to math, and number 5 is sum. And I want to add up these values that I just had fill up L3. So this is my chi-squared test statistic, 24.57, etc. Now we need to get our p-value. Remember we said our degrees of freedom is 2. So once again, here's my test statistic, and I can actually do a copy paste here. So let's go to our chi-squared CDF, second variables for our distribution. Scroll down to chi-squared CDF, and in that, my lower bounds will be the value I just computed. So I'm going to do second answer, and it's going to populate it with that. Then we have a big number, and we had 2 degrees of freedom here. Okay, and you can see, just make sure that that was the last thing that you computed so that it does go into answer. And this is our p-value, 4.6, etc., to the 10 times 10 to the negative 6. I got this backwards, 24.57. There we go. So we had a chi-square of 24.57. Let's bring this back and move it down a little bit so I don't mess up on the values again. And my p-value, the probability that chi-square is greater than 24.57 was equal to 4.614 times 10 to the negative 6. So we can say that this is pretty close to 0, which is less than my alpha. So we will reject our null hypothesis, which stated that the distributions are the same, in favor of saying that they are not the same.